mu of its union equal to this summation. Okay, if we have these two properties, this is the property that call it sigma additivity of mu, and mu of empty set equal to 0. We say this is a measure, but the range of mu was this interval. Okay, in this chapter we see measures that its value are in real numbers or complex numbers. Okay, and it is nu for u, and we see the definition of total variation and also Hahn decomposition. Okay, recall that a measurable space is a pair X and S, where S is a sigma algebra on X. Recall also that a measure on this measurable space is a countably additive function from S to this interval that takes empty set to 0. Okay, countably additive functions that take value in R or C, real number or complex number, give us a new object, call it real measures or complex measures. Okay, real measure or complex measure. So that in this chapter, instead of measures that its value are in this interval, we see measures that maps element in a sigma algebra to real numbers or complex numbers. Okay, dear students, is it clear for you? Mr. Abdul Salam, welcome. Okay. So we have this definition: real and complex measures. Suppose X and S is measurable space. A function such as nu from S to F is called countably additive if we have this equality for every disjunct sequence in S. So that we have this equality for any disjunct sequence in our sigma algebra, A or S for example. We have this equality again. We have this equality again. But difference is in the value of these functions. V is a function from S to F. F may be equal to R or complex number C. This value is not non-negative element. Okay, a function nu, for example, from S is our sigma algebra, to F, R or C, is called countably additive if we have this equality for every disjunct sequence in S. Now a real number, a real measure on this measurable space is countably additive function such as V from S to R, and a complex measure on this measurable space is a countably additive function such as nu from S to C, complex number. Okay, if this F equal to R, this is a real measure, and if we put F equal to complex number, this is a complex measures. Okay, whenever this equality valid. The word measure can be ambiguous in the mathematical literature. The most common use of the word measure is as we define it in chapter 2. Okay, and the terminology non-negative measure would be more appropriate than positive measure, because the function mu from S to F defined by mu of E equal to 0 for every is a positive measure. However, we will stick with tradition and use the phrase positive measure. Okay. Example, let lambda denote Lebesgue measure on this interval. Define nu on the border subset of this interval by this equality. Nu of E equal to lambda of E intersection of E by this interval minus lambda of the intersection of E but this interval. Then nu is a real measure. It is not that Lebesgue measure on R or on this interval is a non-negative measure. Lambda is non-negative on border subset of this interval, but this nu is not necessarily non-negative. Okay, this nu is not necessarily non-negative. For example, if we consider okay. If we consider this function, for any Borel subset of Borel subset of this interval, we define mu of E equal to lambda of zero one intersects by E minus minus 1 0 intersects by E. This is this definition. Okay. Then you can see that this new is countably additive to, sorry, this lambda of minus 1, this interval, okay, minus 1 intersection of this interval by E. And it is very trivial that this nu is countably additive because if mu is countably additive, because if we consider, for example, a sequence as Borel subsets of this interval, and we have this property, this sequence or disjoint, okay, then we see that mu of this intersection, mu of this union equal to mu of this union intersection by this interval. It's very trivial because all of these are subset of this interval, so that these two are the same. This is a subset of this interval, okay? This union is a subset of this interval, so that these two sets are equal, okay? Now, we can write this equal to this union intersection by these two, zero one union by minus 1 and 0, okay? Let me write the internal parentheses by another color. okay, mu of this equal to mu of this, because this interval equal to this union, okay, and this is equal to mu of this union of En intersection by 0 1 and En intersect by minus 1 0, okay, mu of this, and all of these sets are disjoint, so that this is equal to so we can use at first this definition, okay, we can use this definition and write mu of this union equal to this subtraction. Let me write, it is better that we use our definition, okay, and then write these sentences for this, okay, this equal to okay, lambda of this 0 1 minus lambda of this intersection by minus 1 and 0, okay, this is by this definition we replace E by this union, okay, E by this union. Now it is equal to the first term equal to this union intersection of E and 0 1, okay, n from 1 up to the infinity. And the second is this set, the union of en intersect by minus 1 0. Okay, minus 1 0. And this lambda equal to this summation because lambda is a measure. The summation of this intersection and this equal to this summation, lambda of this intersection, minus 1 0, and from 1 up to the infinity, and this equal to this. And this is equal to this summation minus this. N from 1 up to the infinity, lambda of this. And this is equal to the summation of nu of En, because this is nu of En by this definition. Okay, if you replace E by En, we see that this equal to nu of En. Okay, so that this nu is countably additive, but please note that this nu or this measure is not necessarily non-negative. For example, if we consider nu of this interval minus 1 up to this, it is equal to lambda of 0 1 intersect by this interval, and this is empty set. Okay, minus lambda of minus 1 0 intersect by this interval. This is empty set, so that this is equal to 0, and this is equal to this interval, lambda of this interval, and this is equal to 1 divided by 2, so that this is minus this, so that mu is negative number. Okay. If we consider this interval -1 up to this, and if this is origin and this is 1, we see that the intersection of this interval with this interval equal to this, but intersection of this and this equal to empty set, so that this lambda equal to 0 and this equal to the length of this interval equal to 1 divided by 2, and we have this minus, so that mu of this interval is a negative number. Okay, it is negative number. Dear students, do you have my voice? And do you see image? Okay. So that mu is a real measure, not non-negative measure. If mu1 and mu2 are finite and positive measure, then this is a real measure. This is a way to construct real measures. Subtraction of two positive measures is a real measure. And also this is a complex measure. If we choose two real or complex numbers, this is a complex measure. And if nu is a complex measure, real of nu and image of nu are real measures. Okay, this is the relation between non-negative and real measures and complex measures, and these facts are very easy. It is write the proof of these two statements. Okay, it is right the proof of these two statements and send to me this and this. Okay, this and this. Let me write for you. Okay.
من فضلك أرسل الإجابات على هذين الاقتراحين.
It is clear? Okay. Note that every real measure is a complex measure because R is a subset of C, okay? Note also that by definition, infinity is not an allowable value for a real or complex measures because we consider nu as a function from S to F, and infinity is not a member of real or complex numbers, so that in real and complex number nu of E is not infinity. Thus, a positive measure is a real measure if and only if mu of x be finite. Okay? Some authors use the terminology sign measure instead of real measure. Some authors allow a real measure to take on the value infinity or minus infinity, but not both, because the expression infinity minus infinity must be avoided. Okay. In our definitions, real or complex number is not infinity. And this is important. For positive measures, we have to make mu of empty set equal to 0. Part of the definition to avoid the function mu that assign infinity to all set including empty set, but infinity is not an allowable value for real or complex measure. Thus, nu of empty set equal to 0 is a consequence of our definition rather than part of the definition as shown in the next result. Suppose nu is a complex measure on a measurable space x and s, then we have these two property, nu of empty set equal to 0. This is very nice because we see that in the non-negative measures we assume that mu of empty set must be 0, but in complex measures or real measures we don't assume this condition. Only we say that mu must have this property, countably additive. Okay, we don't assume that nu of empty set equal to 0, but this condition automatically hold. Nu of empty set automatically must be equal to 0, and also this summation must be finite for every disjoint sequence in S. Summation of absolute value of this nu. Okay. Please note that nu of Ek is a real or complex number and we take its absolute value. This summation is finite, and the proof of these two are very easy. For example, we see that empty set equal to the union of these empty sets, so that we have this, because nu is countably additive, And this shows that mu of empty set must be equal to 0, because if this is not non-zero, this summation not belong in real numbers. Okay, if alpha is non-zero, let me write for you. If E, if mu is a real or complex measure, then mu of empty set must be equal to 0, because empty set equal to this union. Okay, so that mu of empty set must be equal to this summation. This shows that mu of empty set must be 0, because if alpha or mu of empty set, for example, is non-zero, this summation or this summation equal to this summation. Okay, or this, and this is not an element in real numbers or complex numbers. Okay, because alpha is non-zero and this is not an element in real or complex numbers, and we know that our measure is a function from S to F, and this is a contradiction, so that we have this property in all real or complex numbers. And also the second property holds. Let me remove this proof for you, and we have this proposition: measure determined by an L1 function. Suppose mu is a positive measure on a measurable space X and S, and H belongs to L1 of mu. Define mu from S to F by this equality: mu of E equal to this integral. Okay, mu of E equal to the integral of H on E, not whole of X. Then mu is a real measure on this sigma algebra, and if f equal to real numbers, it is mu is a real measure if f equal to r, and is a complex measure if f equal to c, so that we can construct a real measure or complex measure by this method. We consider a positive measure and define a real or complex measure by this equality. And this proof is very easy. This proof is very easy, okay? But this proposition is very important. Suppose mu is a positive measure on S and H belongs to L1 of mu. We define mu from S to F by this equality. Mu of E equal to this integral. Then if F equal to R, this mu is a real measure, and if f equal to complex number, this is a complex measure. This proof is very easy because for any disjunct sequence in S, mu of this union equal to this by our definition. Please note that we must put instead of E this union. Okay? Please note that mu of E sorry mu of E equal to the integral of f d mu on E, and this is equal to phi of E dot f d mu. This is the definition on E. Okay, now if we consider a sequence in our sigma algebra with this property, this sequence are disjunct, okay? Then mu of this union equal to integral of f on this union, and this is equal to phi of this union, phi of E, okay? And from 1 up to the infinity dot f d mu, and this is equal to the integral of this summation dot f d mu. It is very trivial because phi of this union equal to this summation of characteristic functions. By this property also we must use this property. This sequence consists of these joint elements. Okay, so we have this equality, this characteristic function equal to the summation of these characteristic functions and now we can write this equal to this integral phi of en dot f, okay, d mu. So we see that mu of this union equal to this integral. And the integral of this summation equal to this summation. This whole by the dominated convergence theorem. All of this less than this function. Let me write this for you. But if we have this equality, we see that our proof is complete because this equal to this, and so mu is a countably additive function. But why the reason of this? Why this is equal to this, the summation of integrals? It is very important. Okay, d mu n from 1 up to the infinity. The reason of this is very important. This holds by dominated convergence theorem. Let me write this for you. And from 1 up to the infinity. Please note that for a star, the integral of this summation d mu equal to the integral of this limit of phi en, for example, dot f n from 1 to k and then k tend to infinity. Okay, this series equal to this limit d mu. Let me choose another color such as this or this. Okay, okay, this parenthesis equal to this parenthesis, So that this integral equal to this integral. But this is equal to the limit of this integral. N from 1 to k d mu. And this is equal to the limit of this summation n from 1 to k tend to infinity, and we know that this is equal to this summation. Okay, n from 1 up to the infinity. But this holds by density dominated convergence theorem. DCT, dominated convergence theorem, because if we consider Hn equal to this summation, or Hk for example, Hk equal to this summation, okay, for each k in natural numbers, then we see that for each k, Hk equal to absolute value of this summation, okay, and this is equal to this summation or this function, the union of n from 1 up to the k, because this sequence are disjoint. Okay, this is k. K dot f and this land or f, and f is a function in L1 of mu, so that the integral of this is finite. Now we can apply dominated convergence theorem. This is the reason of this. We can replace, let me continue. Let me continue again. So that the integral of limit of hk d mu equal to the limit of integral of hk. Okay, integral of limit of hk, this is our hk, okay, equal to limit of integral of hk. This whole point DCT, dominated convergence theorem. So we have this nice proposition: for any positive measure we can construct a real or complex measure, okay. Let me express the definition of HD mu. Suppose mu is a positive measure on a complex measurable space and h belongs to L1 of mu, then HD mu is the real or complex measure defined by this, okay, defined by this, so that this measure denoted by HD mu, okay, HD mu is this measure. This is a notation. And we have this proposition: suppose mu is a complex measure on a measurable space x and s, then we have these properties, that these properties are very easy, and the proof of this statement is similar to the non-negative measures, and you can see this. Okay, let me continue in the next session. In the next session, we see the definition of total variation measure. Dear students, do you have any questions? Do you have any questions? Do you have any questions? Okay, we continue in the next session. Thank you very much and goodbye.